Welcome to our third lesson in number theory, or for the chapter 1 preliminaries, the Pigeonhole principle. So what is the Pigeonhole principle? So the Pigeonhole principle was founded by Peter Gustav Litwin Dirichlet, and this was called drawer principle before. And eventually, over time, it was changed into Pigeonhole principle. Now, Peter Gustav is actually a German mathematician around 1834. Now, let us see what is actually the idea or the logic in Pigeonhole principle. Now, the logic in Pigeonhole principle is like this. For example, we have here 10 pigeons. As you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pigeons. And on the other side, we also have here a drawer which has 9 holes or pigeonholes. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Now in Pigeonhole principle, it says that if n, which are the pigeons, are put into the m, which is the pigeonholes, where n or the pigeon are more than the m or the pigeonholes. So there's a hole with more than one pigeon. So as you can see here, we have the 10 pigeons. Now if we put it in this particular pigeonhole, 1, 2, 3, 4, 5, 6, 7, 8. Now there are still 2 more pigeons and only 1 hole. So in Pigeonhole principle, we need to put the 2 pigeons in the 1 pigeonhole. So meaning 1 pigeonhole will have 2 pigeons. So that's actually the logic in Pigeonhole principle. So let's have another example. Prove that if 6 integers are selected from 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 set of numbers, there must be 2 integers whose sum is 15. Now let's say we label the 5 boxes with pairs of numbers that would actually sum to 15. Like for example, 3 and 12 will be 15, 4 and 11 will be 15, 5 and 10 will be 15, 6 and 9 will be 15, 7 and 8 will be 15. Now the next step is every selected integer is placed into the box with the matching label. So with this one, we will actually select at least, also we need to place 6 selected integers into these particular boxes. So since we have 5 boxes and we will be selecting 6 integers, so by the Pigeonhole principle, 1 box must have at least 2 integers. Okay, so let's say we have 3, 11, 5, 9, 7, and 10. So it says here that we can only select 7 integers. So we have 3, 11, 5, 9, 7, and 10. So that's 6 integers. Now it says earlier that there must be 2 integers selected that will sum up to 15. So like for example, since we only selected 3 here on the first box, so it's not 15. 11 on the second box, it's not 15. 9 on the fourth box, it's not 15. 7 on the last box, it's not 15. But on the third box, we have 5 and 10. And if we add it up, it will be 15. So in the application, although simple to grasp, the Pigeonhole principle allows us to prove statements that sometimes seem unknowable. Statements such as, example, common properties in large groups. At any given time, there live at least 2 people in California with the same number of hairs on their heads. So to prove this, we need to establish 2 facts. First, that the population of the California is larger than 20 million. So actually, it's more like 40 million. So second, that it is a biological fact that every human head has fewer than 1 million hairs. So typically, the number ranges between 90,000 to 150,000. Now, to prove this example, or the proof of this example, let A be the set of all Californian heads, and B is the set 0, 1, 2, 3, 4 up until 1 million. So, the AB for which Fx is equals to the number of hairs on the head of X. Since A is greater than B, so the pigeonhole principle asserts that if F is not injective, thus there are two Californians, X and Y, for whom Fx is equals to Fy, meaning they have the same number of hairs on their heads. Okay. Alright, so aside from the pigeonhole principle, let us also discuss infinite sets. So what is infinite set? So infinite set is actually, if a set is not finite, it is called an infinite set because the number of elements in that set is not countable. So when we say infinite sets, it's not countable. And also, we cannot represent it in roster form. Thus, infinite sets are also known as accountable sets. So the elements of an infinite set are represented by 3 dots or the ellipse. Thus, it represents the infinity of that set. So for example, or the examples of infinite sets are a set of all whole numbers. So why is it the set of all whole numbers? So again, it's actually infinite. We don't know when will this particular numbers end. And then a set of all points on a line. So if you actually create a line, so there are the points there will be infinite. Then the set of all integers. So these are the infinite set.